Hello everyone. In this video we're going to be discussing chemical reactions and all the fun stories they have to tell. And so the first thing when we start talking about chemical equations, they're just basically the shorthand notation that we use in order to describe these chemical reactions. So whenever we kind of talk about these chemical equations, they normally have all these qualities. Sometimes some are left out, but again, it's all necessary if you want to fully talk about these chemical reactions. So the first thing that is completely necessary is the correct formulas. And so as I kind of stated in the past, not always will I give you CH4 and O2. I will say something like methane plus oxygen. And so you need to be able to convert those, like the nomenclature, convert those words into proper symbols and formulas. In addition to that, you need to have the correct number, like relative numbers of reactants and products. What I mean by that is you have to have the math correct in order to end up with the actual compound you want to end up with. For example, just because I want water, if I start mixing hydrogens and oxygens together, I might end up with hydrogen peroxide. That's poisonous and you do not want to drink that. But you need to make sure you have the correct amounts that are going to mix together properly to give you the product you're actually trying to go for. And the last one here, the states of reactants and products, sometimes those are left off if it's not that important, but sometimes they are necessary. And by states of reactants, I mean solid, liquid, or gas, and then this additional term of aqueous. And so aqueous just means you had a solid, you dropped it into water, and now it's just floating around in water. And so the reason why that's important is something like dry ice or carbon dioxide. And so carbon dioxide is completely different chemical reaction, or sorry, chemical characteristics if it's gaseous CO2, like what's around us at all times, or if it's solid CO2, like dry ice. And so sometimes the solid, liquid, gas, it's necessary, but that's one of the items that you'll probably see left off occasionally from chemical equation to equation. And so once you have those characteristics, and once you have your correct chemical formulas, and whenever you have the correct relative numbers of these things, you can actually use these chemical equations to do a lot of, well, I say fun math. I think it's fun, but you can use it to do a lot of math in order to figure out pretty much everything about each one of those components of that chemical equation. So before I move on, I just want to make perfectly clear what I'm referring to when I say reactants and products. And so reactants are always going to be what you begin with. They're always going to be the guy on the left side of this arrow. The products are always going to be what you're going to end up with. And so even if you wanted to reverse this chemical reaction, you can't. But if you wanted to and add H2O plus CO2 to give you gas or methane and oxygen, then again, in this case, you would have to kind of flip that arrow around in order to kind of change reactants and products. The reason for this is reactants react in order to produce products. And so in this case, reactants are always going to be your beginning material. Products are always going to be what you are trying to produce in the long run. And so this equation should look a little bit funky. And the reason is it's not balanced. And so one of the key things you have to do anytime you come across these types of problems, word problems or any types of stoichiometry problems, which we'll talk about here in just a minute, you need to make sure your equation is balanced before you begin doing anything. The reason for that is if it's not balanced, then you're just wasting your time because your answer is definitely not going to come out correct. And so by balanced, I mean in order to not defy any laws or chemistry laws, the law of conservation of matter states that you cannot create nor destroy matter. You have to have the same amount of atoms on the left side of that chemical reaction as you do on the right side. And so if you take a look at just the oxygens here, on the left side we have this O2 which contains two oxygens. But on the right side we have CO2 and H2O. The CO2 contains two oxygens and the water contains one oxygen. And so according to this chemical equation, the way I have it written now, some oxygen just magically appeared out of nowhere in order to kind of finish this thing off. But that's not it. Let's look at the hydrogens even. And so on hydrogens on the left side, we have a CH4, which has four hydrogens. On the right side, we have our water molecule that only contains two hydrogens. And so here, somehow miraculously, two hydrogen atoms just kind of blinked out of existence, which again creates a black hole. That's not always a good thing. So in order to fix this equation, we need to use what they call a coefficient. And so the coefficient of 2 needs to be entered in front of our O2 and in front of our H2O. In this case, now we are looking at two O2 molecules and two H2O molecules. So one thing I have to be clear on these coefficients is I am not changing the chemical formula. I am not changing the molecules that it is representing. I am just saying that I need more O2s than what is being initially represented. So please do not try to do weird things like change O2 to O4 or change our water to H4O2. It can't work out that way. Whenever I first told you I am mixing CH4 plus O2, that's what I'm telling you have to do. You can't change that O2 to something else just to suit your needs. And the last thing, which I know a lot of you love to just not even think about it, skip over, but just check your work. It's very easy in this case, just count atoms. And so here to check out on carbons, we have one carbon from our CH4 and one carbon from our CO2, so we have one carbon on both sides. Similarly with our oxygens, we have two O2s, and so we have four oxygens on the left side, and we have two H2Os, and so we have two oxygens there, and then two oxygens coming from our CO2, so four total. And the last one we have is CH4 contains four hydrogens, and our two H2Os contain our other four hydrogens. So there we know everything's balanced out, everything's looking good here, so we're good to go. And so, this crazy term stoichiometry, unless you actually practice on how to spell it, you can never write it out and spell it correctly the first few times. But basically, all it is just stating that once you have a balanced chemical equation, you can use those relationships to determine anything out or anything that you need to about all the other ingredients or all those other pieces. What I mean by that is if you have a balanced chemical equation, you know the exact amount of both of those products you need to mix together. You also know the amount of products that are going to come out in the long run. You know the amount of reactant to produce one product. You know everything about reactants and products. So in order to kind of illustrate this, let's look at a similar kind of chemical equation, but this time it's balanced. And so if you have C3H8 plus your 5O2 gives you 3CO2 plus 4H2O. And so in this chemical equation, now that it's balanced, you can just double check and make sure that everything is situated here. So normally in this chemical reaction, I am telling you that I am mixing one molecule of my C3H8 with 5 molecules of O2 to produce 3 molecules of CO2 and 4 molecules of H2O. But the problem with that is typically we don't just deal with individual molecules. It's going to be pretty difficult for you to just go out and find one molecule of C3H8 and smash it into 5 molecules of O2. But luckily for us, this is just a ratio. And so it's just saying that there is one of these C3H8s to 5 O2s to 3 CO2s to 4 H2Os. And so if we know that ratio is the same, we can change our molecules to the term mole. Because we know every single mole contains the exact same number of molecules. And so please note, I am not changing anything about this relationship. I'm just multiplying each one of those molecule terms times 6.02 times 10 to the 23. So the ratio is the main important concept here. Normally you will deal with moles and not molecules or individual atoms for that instance. But in that case, we can also go through and say if all of our moles are the same, we need to make sure that our masses line up as well. Because remember, the law of conservation of matter or mass states we can't destroy anything, so our masses have to be equal on both sides. And lucky for us, they are. So, I know a lot of you are starting to get a little bit blurry-eyed and looking at these atoms, so let's talk about something we all love, like food. And so when you start talking about your recipes, if you've never cooked a dish in your life, you probably don't just kind of wing it and start throwing everything into the pot and hope it tastes good. Normally, if you don't know what you're doing in the kitchen, you look for a recipe. And so when you start talking about cooking pancakes, I love my pancakes. But if you start cooking pancakes, you follow a recipe of 1 cup of flour to 2 eggs plus half a teaspoon of baking powder will produce 5 pancakes. And so this situation, you are looking at a stoichiometric relationship between your ingredients and your pancakes. And this relationship tells you the exact number of your ingredients that you need to mix together to get an exact number of product or pancakes. So because this relationship calls for 1 cup of flour and 2 eggs and half a teaspoon of baking powder, you wouldn't just on a whim throw in 3 eggs. Because once you do that, I'm not sure what you're making, but it would be horrible pancakes. And so when you kind of go through and start looking at this, if it tells you that you need 2 eggs for 5 pancakes, that's what you'd use. You would use your 2 eggs to make your 5 pancakes. Or you would have a ratio of 2 eggs to 5 pancakes. And so some of those mornings I get a little bit hungry than like others. And so say that I don't want 5 pancakes, I want more. And so I open up my fridge and I find out that I have 8 eggs. And so from there, you can do some math in your head and figure out how many pancakes you can make with your 2 eggs. And so, sorry, with your 8 eggs. And so we know from this previous slide, our ratio is 2 eggs to 5 pancakes. Or we can use this as a conversion to get us from eggs to pancakes. And using my same old dimensional analysis skills, make sure that eggs cancel out with eggs and we're left over with pancakes. And so dimensional analysis and stoichiometry, you've all done this at some point in your life, regardless if you want to believe me or not. It's happened. And so, same idea when we go back to chemistry. And so a recipe is nothing more than a stoichiometric relationship between your ingredients and your final product you want or you need. And so the stoichiometric relationship in a balanced chemical equation is exactly the same thing. But you need to make sure that everything is balanced, that you are using your 2 eggs and not 14 eggs. And so here, whenever I tell you that H2 plus N2 gives you NH3, just going through, you should say, no, that can't happen. Because on the left side, the way I have this written is you have 2 hydrogens, and then on the right side, you have 3 hydrogens. On the left side, you have 2 nitrogens. On the right side, you have 1 nitrogen. So the best thing I can tell you about these types of problems is practice, 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 and do more practice. The balancing the equations should not be the difficult part, because that should be what takes you half a second to do, because that's going to be the first step in these much more complicated problems coming up in later chapters. So let's do a practice. If I use that equation I just showed you of 3H2 plus N2 gives you 2NH3, and I'm telling you that we have 3 moles of N2 and more than enough H2, how much of the NH3 can we create? So first we have to figure out what relationship we have and what the heck we're even trying to look for. And so in the problem, I give you 3 moles of N2. But at the end, I'm telling you, or I'm asking you, how much NH3 can we make? And so at beginning, I'm in one form of N2. At the end, I want to be in NH3. The only way we can do that is to figure out the relationship between our N2 and our NH3. So from the balanced chemical equation, it is noted that you have 1 mole of N2 for every 2 moles of NH3. And I'm just getting that from the balanced chemical equation. The coefficients in one of N2 is 1, or it's not there, it's an implied 1. And the coefficient in front of the NH3 is 2. And so from there, just set up your dimensional analysis. Here we have our 3 moles, and then use a relationship of 2 moles of NH3 to 1 moles of N2. 1 moles of N2 and moles of N2 cancel out to give us 6 moles of NH3. And so again, just keep your relationships fine, make sure you have a balanced chemical equation. And this is a lot less difficult than some of you are going to try to make it. So, another problem. Suppose we burn 22 moles of C8H18, how many moles of our CO2 would form? And so if we have 2 moles of our octane and we add 25 moles of our of O2, we produce 16 moles of CO2 and 18 moles of H2O. And so as I stated previously, figure out what we are given and figure out what the heck we're trying to convert it to. And so in this particular problem, we are given 22 moles of C8H18. We want to convert it to moles of CO2. So figure out the relationship between C8H18 and CO2, and you see that there's 2 of our C8H18s for every 16 of our CO2. But because we're given moles of C8H18, we know that that needs to go on the bottom. And so, again, set it up so your moles of C8H18 will cancel out the moles of C8H18, like octane. And then just cancel everything out that needs to be canceled out. And so again, you need to be very familiar with this. If not, you're going to run into a whole lot of headaches really quick in these coming up chapters. And so when we talk about this relationship, I've gone from moles of reactant to moles of product. You can also go from moles of reactant to moles of whatever the heck you're looking for. And so in the long run, chemical formulas tell you the conversion between each one of the constituent atoms. So what I mean by that is our H2O is telling us that there's two hydrogen atoms for every one oxygen atom. Whereas a balanced chemical equation will tell us the relationship between every one of the reactants and every one of the products. And so, for instance, we've done a couple times, or at least two examples, of converting from moles of reactant to moles of product, or moles of reactant to moles of other reactant. But we know how to convert from mass to moles because we know the molar mass is a conversion between grams and moles. And so if we know the mass of any one of these things that we're looking for, we can take it one extra step. And so this schematic of mass to moles to moles to mass is going to be something that you are going to be doing almost on a daily basis in this class. You're going to have to convert from mass of something to moles. But as I've stated before, moles is always going to be your middleman. And so if you're ever trapped to convert something into moles, there's going to be some way out with that moles. For example, if we calculate the mass of CO2 emitted upon the combustion of 5.0 times 2 to grams of pure octane. And so same kind of equation that we looked at for the previous example. So the first thing you need to do is figure out what you are given and figure out what you are looking for. And so for this problem, I tell you that you have 5.0 times 10 to the 2 grams of octane. And in the end, I want to know the mass of CO2. But because I am given mass of octane and I would want to know the mass of CO2 at some point in our calculations, you know you need to convert from octane to CO2. And the easiest way to do that is to use the conversion from the balanced chemical equation. And so for this particular problem, I basically said, here is everything you need. You just need to arrange it properly. And so we need to convert our masses into moles first, and then we can convert from moles of one substance to moles of the other using the balanced chemical equation. And once we're at moles of our other substance, convert it back into mass by using the molar mass. And so again, in the particular problems on the exams or quizzes, I will give you these masses. For this one, I'm just going to tell you what they are. And so 5.0 times 10 to the 2 grams of octane is what we are starting with. Grams of CO2 is what we want to end up with. Using the balanced chemical equation, we know the ratio is 2 octanes to 25 oxygens to 16 carbon dioxides to 18 waters. And so using the conversion that's necessary for us, we know that there is 2 moles of C8H18 to 16 moles of our CO2. And again, you can either calculate the molar mass of C8H18 or I'd give it to you in a problem here. But those are the only 3 conversions you need, and those will either, again, be given to you or very simple to calculate with the periodic table. So from there, just line everything up appropriately. If we want to go from mass to moles, we need to use the molar mass. If you want to go from moles to moles, you need to use the balanced chemical equation. And again, going from moles to mass, you need to use the molar mass. And so the next thing is just to set it up appropriately so everything cancels out the way we need it to. And so in this previous one, the problem, I give you 5.0 times 10 to the 2 grams of octane. So we want to go from grams of octane to moles of octane. We need to use the molar mass of octane and set it up so grams cancels out with grams. And the next step is to go from moles of octane to moles of CO2. So use the balanced chemical equation, and it tells you that there are 16 moles of CO2 for every 2 moles of our octane. You need to put the moles of octane on the bottom because we need to cancel the moles of octane from the previous step. And we're at moles of CO2, go from moles of CO2 to grams of CO2 by using the molar mass of CO2. Because we're trying to get rid of moles of CO2, make sure it goes on the bottom. Grams of CO2 is hopefully the last one that you have left. And so plug everything to your calculator correctly, and you should end up with 1.5 times 10 to the 3 grams of CO2. And so this last slide, I just want to kind of show it to you again because I've mentioned the schematic is just going to keep getting bigger and bigger and bigger. And so at first we started off with mass to moles by using the molar mass. And we go from things to moles by using Avogadro's number. But now all this is really saying is that if you have a balanced chemical equation, now we can go from mass to moles to moles to mass, from mass to moles to things, or things to moles to things. There's a wide variety of directions you can take with all of this. And again, this schematic is just going to keep getting larger and larger, so appreciate it in small size for now.